parametrized curve in 2D, two dimension. We have the x and the y components being controlled by the function of t, and t goes from 0 to 1. You can think t as time, or t is just parametrized that would act like a connector between the coordinates value. Okay, so now the question asks us to find the length defined by this parametrization for t goes from 0 to 1. So how are we going to do that? First we may try to lay out what we have first. Is that we have previously the equation for a length of a parametrized curve, which is the integral. Alright, so now we have this equation. Well, what are we going to do, right? So this equation applies. Okay, so now let's start with taking derivative of each function. So here we have is 12t squared, and is greater than or equal to 0 with every t belong to the interval 0 to 1, and y prime t, that is 6t greater than or equal to 0 with every t belong to 0 and 1, from 0 to 1. So this, well, we know that since the derivative is always greater than 0, greater than or equal to 0, except at 0 it is equal to 0. So we know that for any points other than 0, you know that x is increasing and y is increasing. So you know that this curve will not intersect itself. You can think of it as like when you have a curve and it's always, the x direction is always increasing for any particular time t, and y, the horizontal component, is always increasing. So it only has one, or not a lot of direction to go, but to go up and advance upward and advance to the right, based on the coordinate system. So we go ahead and graph it and see if this is like what we expect. All right. So we know that from this we know that the curve will not intersect itself. Not intersecting itself. So that when we know that we can operate this this equation right there with no complication at all. So this is just an example, just so we can apply that. Okay. So we have this. We may try to plug in some points maybe. So let's try to plug in some points like. So we have t 0, 1/2, and maybe 1. Okay, all right. And for x 0, everything is 0. X and y is 0. For 1, for 1/2, it is this one of the a's is 1/2, right? X is 1/2, and this is 1/4, so 3/4, and at 1, this is x is 4 and y is 3. All right. So we can go ahead and graph it. Maybe it's not a major thing that you don't graph this, but you should graph it so that it gives you a better look at the graph. How's the graph is doing? So we have t 0, 0, 1/2. X is 1/2. Let's say it's 1/2, and 3, 4 out here. Okay, and y 1, 2, 3, 4. Right. Y 3. So maybe here. Right. So you know that it does something like this, right? So this, there you go. There's the curve. Okay. So t at this point t equals 0, t equal 1/2, and t equal to 1. All right. So go like that. You can think of time. Time is the best tool to use so that you have a better intuitive thinking of seeing how the graph progress, how the graph is progressing. Okay, so now we just go ahead and apply that into the equation that we have. So we have the length of L will be equal to, we go start from 0 to 1, derivative of that is squared, right? So that 144 t to the 4th. Alright. This is 6t, so 36t squared plus 36 t squared. Alright? dt. Alright. Okay, so what are we going to do about this? Well, we may want to extract out t squared, so we have t outside, right? So let's try it and see what we have. 0, we put out t squared, and we have t times 144 t squared plus 36 dt. Some people may try to use trig substitution in here, but if you think about it, it's just a chain rule being reversed, right? It's just a reverse process of it. So you can go ahead and you can do some substitution, and you can go straight. You may say, oh, that will be 144 t squared plus 36 3/2 times 2 over 3 times 2 over 3. You have a 2 here, but you don't have a 2 here. Therefore, you have times it by 1/2, right? Okay, and it goes from 0 to 1. And this is 1 over 3. So 1 over 3. You put in 1. That's 144 plus 36. That's 180. So times 180. 3 over 2 over 3 minus 0, put in here, that's 36. 36, sort of 36, that's 6. 6 is 6, that's 6 times 36. That is 260. Will be your answer. Just trying to divide it. Right? Thank you very much.